Okay, so in this example we're going to look at how to use tail recursion. So tail recursion, a tail recursive method is efficient. A recursive method is said to be tail recursive if there are no pending operations to be performed on return from a recursive call. However, method B in figure 18.11 is not tail recursive because there are pending operations after a method call is returned. So, for example, the recursive is palindrome method that we looked at is tail recursive because there are no pending operations after recursively invoking is palindrome. However, the recursive factorial method that we saw previously could benefit from using tail recursion. Tail recursion is desirable because the method ends when the last recursive call ends, and there is no need to store intermediate calls on the stack. Compilers can optimize tail recursion to reduce stack size. A non-tail recursive method can often be converted to a tail recursive method by using auxiliary parameters. These parameters are used to contain the result. The idea is to incorporate the pending operations into the auxiliary parameters in such a way that a recursive call no longer has a pending operation. You could define a new auxiliary recursive method with auxiliary parameters. This method may overload the original method with the same name but a different signature, for example, in factorial. So in this factorial example, we have a factorial method stub here, and we're taking in a parameter. In the scanner, we're actually taking in the argument. So the scanner will take in a number, and that number will be passed to the factorial method. Then the factorial method will process that, and it'll take a result. So the result is what gets carried through the recursion. So if n equals 0, it will return the result. The important part about this is that the recursion occurs right here. Okay, so when we take the parameter in here for the number, that's going to get decremented in each recursive call. Then the number that's been decremented will be multiplied by the result that's passed in. So in this case, if we were to count down with 3, what would happen is we'd start with 3 here, and then 3 would get reduced to 2, then 1, and finally it would get reduced to 0, which would return the result. As we restart the animation here, we can kind of see that the program starts the execution from this point here. Then we can work through this. We can enter a non-negative number 3, hit OK. So this is the variable for n. Then we can click next. All right, the program invokes the factorial n. Then we can continue. The factorial 3 is invoked and pushed to the stack. The value of n in the main method is passed to the factorial. Then the program invokes factorial n1. All right, then finally factorial 3.1 is invoked and pushed to the stack. Okay, so it checks to see if this tests the statement to see if n equals 0. It's false since n equals 3. And the program invokes the factorial n minus 1 and n times that result. Continue working through this. The next step is 2 and 3. That gets passed in. And finally, the statement tests if n equals 0, and since it is false, n is equal to 2 at this point, so that gets skipped. We go to the next call, and then the factorial is invoked again. This time we're passing in 1 and 6, and then it tests to see if that is true here in the statement. It's false, so the program gets invoked again. And then we check to see if it's 0. Then it tests to see if it's 0, and it's true since n is 0, and then finally returns the result. In this case, it would be 1. All right. And so finally, after you undo all of the recursion, it goes 2 times 1 times 3, which gives you 6. That's how that works. Okay. So this is the implementation here. In this line we have the factorial, and then we have the result that's being passed in. So the first factorial method on line 5 simply invokes the auxiliary method in line 6. So on line 5, this invokes the auxiliary method in line 6. And then the second method contains an auxiliary parameter result that stores the result for the factorial of n. This method is invoked recursively in line 14. There's no pending operation after a call is returned. The final result is returned in line 12, which is also the return value from invoking factorial n1. So we can check our understanding here. There's a way to rewrite the Fibonacci sequence such that it uses tail recursion. The way to do this is to add an index, and then we need to pass in a result. So the index that we're passing in is the Fibonacci index, then we're passing in the next number and the result. So the thing that we're going to check here is if this index is equal to 0, this is the base case, we're going to return the result. Otherwise, we're going to calculate the index minus 1, and then the next number plus the result, and then next. Okay, I'm going to continue working through this. So we have our word matching exercise. So occurs when recursion does not reduce the problem in a manner that allows it to eventually converge to the base case or not specified. So this is going to be infinite recursion. Is a recursive method that has no pending operations to be performed on a return from a recursive call. So is a recursive method that has no pending operations to be performed on a return from a recursive call. Okay. Tail recursion. Is the simple case on which the problem can be solved immediately is also called the stopping condition. This is the base case. Is a recursive method that is used to help derive a solution from the original method. Okay, we'll skip that one. Is a method that directly or indirectly invokes itself. So this is going to be direct recursion, indirect recursion. Sorry. So we'll have to come back to that one. So occurs when a method A invokes method B, which in turn directly or indirectly invokes method A. So occurs when method A invokes method B, which in turn directly. This makes more sense for direct recursion. Okay, means that a method directly invokes itself recursively. Direct recursion. Occurs when a method invokes method B, which in turn directly or indirectly invokes method A. This could be indirect recursion. Is a recursive method that is used to help derive a solution for the original method. This is a recursive helper method. And then we also have another recursive method. Here we go. Okay, so here we go. That's tail recursion, and I hope that you enjoyed watching this. Thank you.